All right, continuing on with enolates, we learned in the last lesson how to generate an enolate that the most acidic hydrogen is the alpha hydrogen, not the aldehyde hydrogen, for example. And once you have a base like LDA or ethoxide, hydroxide, methoxide, some kind of a base, it's going to grab this one of the alpha hydrogens and make an anion on the carbon, and that's your enolate ion. And there is a form where you can show the negative on the O through resonance. You could do that, but we're not going to do that because most of the reactions we see are addition to the alpha carbon, and that has to do with compatibility with electrophiles. Most electrophiles we see are going to prefer, or they're going to be what we call soft electrophiles. And they're generally going to prefer attack from the alpha carbon. So start with a carbonyl compound, identify alpha hydrogens. If you see a base, we make our enolate. That's the first step. Then we have a series of different kinds of electrophiles. This one here is our typical alkyl halide, which you've learned a lot of, like SN1 and SN2 reactions. We've got an electrophilic carbon, such as in an alkyl halide where we have a dipole this way. Okay, so that makes this R group very electrophilic. So then the enolate attacks there. And we can have carbon-carbon forming reactions now. Okay, so this one is going to have now a new group. Let's say this is all in blue. Okay, and now I can have a new carbon-carbon bond right here. All right, so isn't that great? Okay, we've had Grignard reactions that do carbon-carbon bond. We've had cyanide. So there's lots of ways to, or let's see, also the terminal alkyne makes the acetylide ion. It's probably good just to make a note of these things. The acetylide ion has been our carbon nucleophile in the past, as well as cyanide. Okay, so different ways of doing this, and also, of course, our Grignard reaction, another kind of nucleophile there. Okay, so these are all things that we've used before as nucleophiles. Now we're going to add the enolate to our list of carbon nucleophiles. All right, so let's take a look at this reaction. We've got alpha hydrogens. So of course, how do we make our enolate? We're going to use a base and we're going to deprotonate that. Form our enolate, and now we're using a different kind of electrophile. This time we're using bromine, so Br2. So we could pretend like this is polarized at any given time. There's an induced dipole or instantaneous dipole that can form. So this will attack here, and then we'll have alpha bromination. So alpha bromination, or bromine added to the alpha position if we do this reaction. Now let's say we're trying to do only one bromine. We don't want to have two bromines. The problem with this is that this alpha brominated product will actually be very difficult to stop at the alpha, at the monobrominations. So what that means is we actually generally tend to see multiple brominations occur. So if you wanted only one bromine, it's very difficult to do this reaction and only get one bromine. It's more likely that you will get two bromines instead. So can we explain why that is? Well, if we have excess base, then you're going to have the base keep reacting with all the alpha hydrogens. So we're going to get the enolate again, and then you're going to have another reaction where you have then the second bromine attack. So the unwanted side product will be the dibrominated product if your monobrominated is what was desired. So why is that again? It's because we have base and it continues to react with the alpha hydrogens. So to avoid that, let's say that we want a way to only make the monobrominated. Okay, so I don't want excess bromine, I don't want base. I have to figure out a way to do this in acid. So there is a reaction with acid where we see a significant amount of monobromination. So let's figure out a mechanism for how an acid conditions work. So for this one, we'll probably do what we have done in the past, which is protonate. And one clue for this is that we're going to use acid to have an enol, and the enol is going to be, we won't be able to generate enolate, but we'll be able to generate enol. And if you remember back to the very first thing we did in this new chapter here, we had acid catalyzed enol formation, right? So let's do that, and then we'll use our enol as a nucleophile. So at this stage, we've got our enol via acid catalyzed tautomerization or enolization. And I can use this now as my nucleophile. So yeah, it's not as great as having an enolate ion because this is neutral, whereas our enolate ion was negatively charged. So this is definitely a stronger nucleophile, but this will still work. And what we'll get is we'll have Br2, and this will come down and attack there. Okay, so then what we have is plenty of water in solution to deprotonate this, and then we've got our monobrominated product right there. And it's a net loss of a Br minus and an H plus, so they say plus HBr. But remember, this is strong acid, so it's mostly dissociated. Now, when an unsymmetrical ketone is used, there's some regioselectivity with this reaction. What we find is that the major product actually monobrominates at the more substituted carbon rather than the less substituted. So do you think steric hindrance is a factor here? Well, it doesn't seem to be the predominant one. So if steric hindrance was an issue, we would predict that the addition would happen, the major product would be here, right? Where to avoid the steric hindrance of the methyl. So steric hindrance is not the important factor. In acidic conditions, it's probably more of a stability thing or electronic thing. So let's take a look at this mechanism again and see if that can help us explain that. Notice that the double bond is what's attacking. So wherever that double bond is more stable, that's probably where it's going to form. So we have the possibility of a double bond forming here if we remove this alpha hydrogen, or we could have the double bond forming here. Which double bond would be more favored? So the alkene is more favored when it's more substituted. So we would probably make this enol right here, and then have the attack and show the bromination occurring at the more substituted alpha carbon. So the more substituted alpha carbon is where we'll have the nucleophile form because that's from the more stable enol. Which reagents would you use to synthesize the following? So before we do this, I want you to have this reaction written down as one of the reactions for today. Okay, so far you have enol keto tautomerization, you have enolate formation. This was from the last video. Today we're going to start with this reaction here, so make sure you write down that. And you can also write down this one as well, but remember this one's going to give you multiple brominations. So when you write this one down, make sure you write this as the product. Okay. You can also write this reaction where you have an R group from an alkyl halide attached. So you have, for today, this reaction, but with this product, and then this reaction with the monobrominated product. So those are the reactions to work with so far. So now think about that and think about how you might do this reaction here with the concept that we've learned how to put bromine here. So then you need to take it to that level and then one more step. All right, so for this one, of course, we need to oxidize this alcohol to a ketone first, and then we just learned how to brominate it, right? So we're going to put a bromine here, and so that uses up the reaction we just did, and then finally we just need to eliminate the Br and make a double bond here, pi bond. Okay, so our sequence of steps is going to be first oxidation, so Jones or sodium dichromate, okay, in acid, all right, or KMNO4, okay, and then we have alpha bromination, but monobromination. So I'm going to use acid catalyzed bromination here, And then our last step is not something we covered now, but something you should be aware of is that I just need an E2 elimination. So I just need base to come grab this H and lose that leaving group. So I want to just use step 3, strong base and heat. All right, and I don't need a bulky base or anything. Any kind of strong base will be fine. Okay, so that's an example of E2 elimination from first quarter OChem. All right. Okay, so let's try this one as well. So go ahead, same ideas, and go ahead and give that a try. All right, so for this one, you need to only oxidize it to the aldehyde, not to the carboxylic acid. So you have to use PCC. Okay, so hopefully you saw that. And then the rest of it is the same as above. So we need to do alpha bromination, and then we do strong base and heat. Okay, so same as we did above. All right, so the next reaction that we're going to learn is, what if we have a carboxylic acid and we want to monobrominate that? Okay, so here's my carboxylic acid. Before, I had an aldehyde or a ketone, mainly ketones up here, but also could be for aldehyde. Okay, so that's the difference, is the functional group that we're starting with. You might ask, well, why do we have to have a special reaction if it's a carboxylic acid? And that's something I want you to think about as we go through the mechanism. Okay, so for this one, it's a little more complicated. It's also got a more complicated name, named after 3 scientists, so Hell, Volhard, Zelinsky. And hell is basically how you're going to feel, because it's a lot of steps and a lot of reagents and a lot of reactions in this chapter. Okay, but I hope you see that they're all very similar and build on what we've already learned. So it's not actually that bad. Okay, so PBr3 is used to change that functional group to an alkyl halide. We could also change it to a chloride. So do you remember how to do that? If we had a chloride instead, we could use vinyl chloride, or SOCL, as some people call it. Okay, once we have the alkyl halide, then we can use the enol form of that and do the attack on bromine. And then we can add water and break this down. So these are the steps we're going to use. So the first step, mechanism, we should review. Now we have done a review of carboxylic acids to acid chloride using SOCl2. Why don't we review the one with the bromine? Okay, because it's been a while since we've done that. So for bromine, it works almost the exact same way as for thionyl chloride. So PBr3 looks like this. All right, so what I'll do is same kind of reaction. Okay, so at this stage, I'm going to attack with bromide. And then I'm going to have to lose this guy right here. Okay, so here I could grab here to neutralize that, and now I've got my alkyl halide, which I'll draw properly like this. All right, so remember, this is a good leaving group, and once I have my alkyl halide, now I want to turn this into an enol, and after I get the enol, then I can attack the Br2. Okay, so that is going to be our alpha bromination. And then our last step is going to be a water workup here, and it's actually going to change our acid halide is going to react with the water, because acid halides are very reactive, especially with water. Okay, so I'm going to show H2O coming in here, and I'll do 2 things. It'll neutralize this first of all, and then it will also attack, once I've neutralized that, it will attack the carbonyl. And we'll have the leaving group leave here. And then we'll have to do a neutralization step so that we end up with our carboxylic acid. Okay, so eventually I'll lose a hydrogen off that OH to make it an OH2 to make it an OH group. Okay. All right, so I didn't show every single step. I'm just missing a proton transfer here, but hopefully you see I've run out of space. In order for this reaction to work with a carboxylic acid, we had to convert it to an acid halide first. And the reason why we had to do that is because you cannot get an enol very easily from the carboxylic acid directly. That is, in this reaction, whenever you have your starting material, we've been using, and enol to react this. So the enol that we would need if we were to use the carboxylic acid would look like this. And it turns out that the enol from carboxylic acids is not as stable as the enols from aldehydes and ketones and even acid halides. So for that reason, it's much better to go through an acid halide first, which can then easily be converted back to carboxylic acid later. So let's try practicing these reactions. So add this one to your list then. And so we've got alpha bromination of carboxylic acids in addition to the ketones and aldehydes we saw earlier. And let's see how we can use those in these synthesis problems. So for this first one, we can think of this in one of two ways. We could think of it as, this piece plus a 1 carbon unit that sort of looks like this, or will look like this when it's done attacking. So we could think of this as the nucleophile, and maybe think of an electrophile that this group could add to. Or the alternative, which is this could be the nucleophile and we add it to here, and this will be the electrophile. So either way. Now it makes more sense to me that this would be the electrophile because it's got a carbonyl group. That's usually not a good nucleophilic carbon, right? So there is a way to change this carbon here to a nucleophilic carbon, which is to do a Grignard reaction. So let's draw that out. Now at this stage, we need to think of how to get this 1 carbon unit into a carboxylic acid. Most students forget this reaction, but all you need is CO2. And this is something, if you took my OChem 2 class, that you actually did in the lab for the Grignard reaction, we added dry ice, which is CO2. That's how we got carboxylic acid. You can see the mechanism here, attack the carbonyl of the carbon dioxide here, and then you end up with a carboxylate ion. So after this first step, which is add magnesium to make our magnesium bromide, which is a Grignard reagent, then second step will be add CO2, and third step will be to work that up with water or dilute acid to neutralize it. And then after that, we need to alpha brominate it, right? Because here's our bromine there. So in that case, we can use the reaction we just learned, which is I have a carboxylic acid to start with. So I can't just do acid and Br2. I have to do the Helvol-Hard-Zielinski reaction, which is, so finishing up. So step 3, don't forget, it's just dilute acid and water. Step 4, I just need to look back here. Remember, we did PBr3 or SOCl2, and then Br2, and then water. So those are 3 separate steps. And then step 4 would be PBr3, Br2, and step 5 would be water. We have to have step 5 separate because water will break down the acid halide too soon. All right. So that's that reaction there. Okay, so go through this and see if you can figure out the rest of these. And your key will be to how to turn these into carboxylic acids first of all, and then you can apply Helvol-Hard-Zielinski. All right, so we're back, and the next one's easy. It's just Jones reagent or sodium dichromate or potassium permanganate. So we make the carboxylic acid first. Then to brominate the alpha, we can use the Helvol-Hard-Zielinski reaction. And the last one is trickier. Students always forget this one. Cyanide, cyano group or nitrile group. You can hydrolyze it with acid and heat. So that will make the carboxylic acid there. Then you can do the Helvol-Hard-Zielinski reaction. And if you forgot how to do that, that was a mechanism in the last chapter. That was with, if you recall, that was a cyano group, so CN. And remember in acid that this got protonated, and then we replaced the N with oxygens and then had an additional OH group. So revisit that reaction if you forgot. So the last reaction we're doing in this section is called the Haloform reaction. And in this reaction, let's say that you have a methyl ketone. You can actually replace these methyl group hydrogens with bromines in a way that will cleave that off and leave you with a carboxylate, okay, or which can then be neutralized to carboxylic acid. So to do that, we use a base, and we get multiple brominations to this, to here. And then you do that again, okay? So you brominate all of the positions possible, and then you can cleave that off. And let's show a mechanism for this. So let's say that you know how to get this far, which is how. Let's see, you do this, and you make your enolate, and then that enolate attacks the Br2, and that's how you get bromination, right? So now that we're here, let's say that we do that again. And once we do that, and let's say that the other side of this is not necessarily, let's say this is just not a methyl part right here. Okay, so as we do that, once we brominate again, then we have this very electron withdrawing situation here, right? This carbon here is getting electron density pulled toward all the bromines. So that makes this carbon very electrophilic right here. And what happens next is that hydroxide will come in and attack that carbonyl carbon now. Now it's sufficiently electron withdrawing enough that will come in, and then we'll make a tetrahedral intermediate and lose this group. All right, so that seems really unusual, right? We haven't learned about this leaving group yet. So that's because of all the bromines. So what happens next is that when this leaves, it will get protonated right away by, let's say, water in solution, since sodium hydroxide is usually in water. Okay, and then we have our haloform, which is carbon with 3 halogens on it. Okay, so this is bromoform. Usually in the past, historically, this reaction was done with iodine, because the iodine haloform makes, or iodoform, makes yellow precipitate. So you could see a test for whether you have a methyl ketone. That was very useful for that. So these are supposed to be bromines. So we have CHBr3, and then we have this carboxylic acid. However, this is in basic solution. So with the remaining OH minus in solution, generally we see that the conjugate base form is usually favored in a basic solution. So technically, until we neutralize this, we're going to see the carboxylate form of that carboxylic acid. So if you need a carboxylic acid, though, all you have to do is just work this up with more water or dilute acid. Okay, so here you could form, after another step, just with H2O, you could form the carboxylic acid. All right, so overall, what are we doing? We're taking a methyl group that was here, and we're replacing it with hydroxide group, which hydroxyl group, which is in its basic form and in basic solution. So for these problems, I want you to think about, well, first of all, write this reaction in your list of reactions. So it's a methyl ketone of some kind where you have NaOH/Br2, and that will make these products at the end. Okay, and this can be further neutralized to make a neutral carboxylic acid. So keeping that in mind, methyl ketone to a carboxylic acid. Let's see how we can use that reaction for these problems. Let's do one of these together. So first one is we have an alcohol. We're trying to make it into an ester. So one thing I could do is probably need to oxidize it to a carbonyl, because that's what we're generally starting with. So once I oxidize that, maybe I'll use Jones reagent or KMNO4 or sodium dichromate. Notice that what I get is a methyl ketone. So that is what I'm going to use the haloform reaction on. So I'm going to use NaOH and Br2. So far I have, let's say I use KMNO4, and then I just do oxidation Jones or KMNO4. NaOH and Br2, we just learned, puts all the bromines on here, and then that NaOH attacks it and that leaves. Okay, so That's the haloform reaction we just did. And then we just need to learn how to do that. And I think we did that last time, right, in the previous chapter. So we'd change a carboxylic acid to an ester, either through changing this to maybe acid chloride and then adding ethanol, or just acid catalyzed esterification. All right, so I would like you to practice using this haloform reaction in these problems down here as well, and we'll go over them in a few minutes. All right, and one thing I forgot right here, by the way, is I forgot to add our water workup or our dilute acid workup to get the carboxylic acid instead of a carboxylate. So I'm just going to add H3O plus here. So that should technically be step 3, and then I would do step 4, H plus and ethanol. So maybe you forgot to do that as well. So first thing here would be ozonolysis to get cleavage and get our double bond O methyl ketone. Then we do the haloform reaction with the acid workup to get carboxylic acid. And then SOCl2, thionyl chloride, to get the acid chloride. Next one would be acid to get this, acid and water to get this back into the carbonyl, which makes it a methyl ketone. So we can do the haloform and then acid workup to get the carboxylic acid. Last one is an imine back to the carbonyl. So we have to reverse the reaction. Instead of acid with amine, we need acid with water. So we do that. And then do the haloform reaction because I have a methyl ketone here. And then after acid workup, I do thionyl chloride, and then I do ammonia, and I get my amide. Okay, so those are it. Okay, so I would write a list of these reactions, all right, and then practice mechanism and synthesis with these practice problems.